This is the second short video in our series, the 4.5 biggest fallacies about black holes. Black holes are often represented as though they are the ultimate cosmic vacuum cleaners, sucking up everything in their vicinity. In this video, I would like to put this myth to bed and present a better understanding of what a black hole really is. What I am going to say will give you a different way to look at black holes and possibly a new insight into the way that gravity operates. The first step is to travel back in time to visit Isaac Newton in his rooms in Trinity College, Cambridge. Newton proposed that every piece of matter in the universe attracts every other piece. This is his universal theory of gravitation, universal because it applies to all matter everywhere. It was designed to answer a number of key questions. How is the Earth glued together into a sphere? And similarly, how are the Sun, Moon and planets held together? What causes an apple to fall to the ground? Newton's other goals were to explain why the Moon orbits the Earth and why the Earth and planets orbit the Sun. But Newton's theory was not simply a rough idea about how the universe might be constructed. It was an exact prescription for the strength of attraction between any two particles of matter. In particular, according to Newton, the gravitational force is given by this formula, where m1 is the mass of the first particle, m2 is the mass of the second particle, g is Newton's constant, and r is the distance between the two particles. The formula says that the bigger the masses, the bigger the force, and also the closer together the two masses, the greater the force between them. More precisely, gravity falls off with the square of the distance between the two particles. Doubling the distance reduces the force to a quarter of its original value. Tripling the distance reduces it to a ninth, and so on. This is known as an inverse square law. You may well be familiar with all this, but it is the next step taken by Newton that I would like to focus on. Often it is presented as though it were obvious, but this is far from the case. Newton faced a big problem. If every particle of matter attracts every other particle of matter, how could he possibly calculate the overall effect of such a multitude of forces? We could estimate the size of the gravitational force between the Earth and the Moon by slicing the Earth and Moon each into 1,000 pieces, and then calculate how each piece of the Earth attracts each piece of the Moon. That would give us 1,000,000 forces that we must combine, and the size of each would be different as the distance between the chunks of matter varies. How could we possibly perform such a calculation? Fortunately, Newton was an outstanding mathematician, and he had already invented one of the most powerful tools in the history of mathematics, calculus. With this tool, Newton could dramatically simplify his problem, but only in the very special case of an inverse square law, which is lucky because this is exactly the case he was interested in. Newton showed that the combined gravitational attraction of all the point masses that form a spherically symmetric object, such as the Earth, the Sun or the Moon, is the same as if the total mass of all the particles were located at the exact centre of the sphere. This transforms what would be an impossible problem without a modern computer into a problem that could be solved with a pencil and paper. Now, when considering the gravitational attraction between the Earth and the Moon, Newton only needed to consider 2 points, one with the mass of the Earth located at the centre of the Earth, the other with the mass of the Moon located at the centre of the Moon. Following Newton's simplification, the gravitational force between two spherically symmetric bodies such as the Earth and the Moon is given by this formula, where g is Newton's constant, big M is the mass of the Earth, little m is the mass of the Moon, and r is the distance between the centre of the Earth and the centre of the Moon. Newton's proof is so powerful that this formula is often presented as though it were his starting point. It is certainly the most useful way to express the gravitational interactions of spherical bodies such as stars and planets, but skipping straight to this result sidesteps the fact that it is not correct for other distributions of matter. The formula is only true outside a spherically symmetric mass. It isn't even true within a spherical mass. But what has all this to do with black holes, you might be asking? Newton transformed the horrendously complicated problem of calculating the gravitational forces due to all the innumerable massive particles forming a spherically symmetric body into a problem that is mathematically identical but much easier to handle. We can treat a spherical body as though all its mass were located in a single point at its centre. This is just a mathematical trick, or a mathematically equivalent way of looking at a complicated problem. But there is a physical situation that exactly matches this mathematical idealization. Perhaps you can see where I am going with this. A very massive star may collapse under gravity to form a black hole when its nuclear fuel runs out. When this happens, the star contracts to a point at the centre of the newly formed black hole. The entire mass of the star is now located at a point at the centre of what was the star. The black hole physically matches the mathematical idealization that has been used to model spherical masses ever since Newton. So what does this tell us about the gravitational field of a black hole? It tells us that if a star collapses to form a black hole, then its gravitational field remains the same. More precisely, it is the gravitational field outside what was the body of the star that is unchanged. The gravitational field within will have changed, but this is irrelevant to any external bodies. So if the Sun was suddenly transformed into a black hole, far from metamorphosing into a cosmic vacuum cleaner, its gravitational attraction would remain the same. The planets would continue to follow their well-established orbits. You might be wondering what Einstein's theory of gravity, general relativity, has to say about all this. After all, general relativity superseded Newton's theory over a century ago, and black holes cannot be understood properly without general relativity. According to general relativity, the gravitational field outside a spherical body is described by the exterior Schwarzschild solution. Inside the body, a different solution is relevant, the interior Schwarzschild solution. If the body collapses to form a black hole, then the exterior Schwarzschild solution describes the shape of space-time all the way to the centre of the black hole. This means that the shape of space-time, the gravitational field, outside what was the body of the star remains exactly the same. So just as in Newtonian gravity, if a spherical mass collapses to a point, then as far as any exterior objects are concerned, the gravitational field remains the same. Our aim at the Cosmic Mystery Tour is always to cut through the media hype and focus on the real science. So don't forget to subscribe, and if you have any suggestions for future videos, put them in the comments. Your suggestions are always appreciated. Thank you for watching. I'm Nicholas Mee. May the force be with you. If you would like to know a bit more of what general relativity says about black holes, take a look at this video. How big is a black hole?